Good afternoon, sir.
Good afternoon. Good afternoon, Aryan. Let's start at 3, 4. Let's allow some other people to attend the session as well.
Sure, sir.
So, hello everyone. So, today is our 12th live session of the course Semiconductor Devices and Circuits, which is being taught by Professor Sanjeev Sambhadan. And this will be the last session, which will be problem specific. In the next session, hopefully, we will solve the problems from each of the topics, hopefully, that we have gone through in this lecture. Like we will start from the, let's say, the quantum mechanics. We will select one problem from the quantum mechanics part, and then moving to the uh, like to the circuits at the end. There will be one problem, so like that sort of from the circuits as well. So in this will be our last specific session, problem specific session. Like this session today will be oriented towards the circuit application only. So let's start our 12th live session. So basically, for this problem, which says that when used in an amplifier circuit, a MOSFET is generally biased in. So let me ask you people, since I have given the answer as well in this slide, so you normally hear that we have to operate the MOSFET in the saturation region generally. So why is that thing? Why should we operate this MOSFET in the saturation region? There must be some reasoning behind that. So let's go a bit deeper into this concept, why we should bias this MOSFET in the saturation region. Okay, first of all, let's turn off the video and let us begin. Okay, so they, for example, if I am having any, for example, if I need, for example, any power amplification sort of a thing, so how can I get the power amplification in any network? For example, if I use passive network like resistor, there won't be the what I can say, there won't be the amplification of the power, because there will be the dissipation in the resistor itself. There is some issue with my network as well today. I'm sorry for that. That's why I am turning off these videos, because this allows me to save the on this speed part. It results in the better quality of the audio. I'm sorry for this. So basically, I was talking about this power amplification. So these resistive network, for example, this passive network, this won't allow us the amplification, because there will be, as we know, there will be the power at the output will be less than the power at the input, because of simple resistive losses in the network. So there must be some network what we should look into, which allows us to have this amplification. So this basically, there is a concept that this non-linearity is essential for the this power amplification. If we consider some time invariant system, let's not dig deeper into these terms, and let us just try to get basic insights how we can use this some non-linear system, which we will just by mathematical manipulations we will show that how we can use MOSFET in saturation region as an power amplifier. Okay, for the power amplifications, like that sounds more good or more prominent term for this. For example, if I have some network which is like this, let me draw this black box. Okay, I have some black box. This is some non-linear network. Okay, okay, for example, now I am having this network, and I am having the terminals 1 and 1 dash. I am having some current I1 which is flowing through this network into its input terminals. This will be the bias at the, what I can say, I shouldn't say bias, this will be the input voltage rather at the terminal 1 1 dash. So for biasing, I am having another terminal 3 and 3 dash, which is for this DC biasing. This is our IDC. Okay, this is the DC bias. So this is some VDC. Similarly, I will be having output. Okay, this will be some load that will be associated with this network, and this will be connected to the terminal 2 and 2 dash. Okay, now this current I1, it will be some function of this voltage V1, and if this is the output voltage V2, it would be the function of V2, and it would be the function of this DC bias. Okay, similarly this I2 will also be some function of V1, V2 and this DC bias. Okay, so these are our variables of interest. Okay, variables of interest, as simple as it gets. Okay, it is simple. We haven't done anything specific over here. We have just said if this is some network and the input currents are given by this thing, and we have some small signal which is acting as an input, and we have this DC bias, and we will be having a corresponding output voltage and some current in the output network, and we have simply said that the current in the input will be some function of the input bias, output bias, and the DC bias. Similarly, we have said that the current at the output will be some function of this, what I can say, uh, this our function of these biases V1, V2, and VDC. So if we consider these nonlinear functions, there is no closed form solutions for these. So for these things, these Taylor series, you must have heard this Taylor series comes into the picture. So we know that for these V1, V2, and VDC, we will be having some currents that will be flowing through this circuit. Now if we assume some, for example, some particular value of these biases, for example, this V1 is equal to, let's say, this V1 is equal to V1 0, this V2 is equal to, for example, V2 0. So, and corresponding to that, we will be having this current which will be I1 0, and we will be having this current I2 which will also be I2 of 0, let's say. Okay, it would simply mean that we are knowing the initial position. Okay, we can consider this as an initial guess, for example. So this will be the initial state of our system. We will be having this V1 at the, like, let's say, time t equal to 0. I am starting with this bias. Okay, and V2 will be V2 of 0, and VDC will be simply VDC, because this is a DC bias that we are using to just give particular voltage to our circuitry in order to have it biased in a proper region, in order to bias this device. For example, in case of a MOSFET, we would say whether this bias will operate, make this device operate in saturation, whether it will make it operate in triode region or something like that, or whether it will be in deep, what we can say, off state region. Okay, there can be any region that this bias could drive this circuit in. Okay, so we now know that, let us say that this is the initial state. The initial state would simply be now, for example, sorry, this initial state will now be some function of this I1 0. It would be now the function of this V1 of 0, V2 of 0, and similarly VDC will be constant. I2 of 0, FD, F2, which will be a function of V1 of 0, V2 of 0, and VDC. As simple as it gets. Okay, this we can consider initial, or initial location, or initial condition, whatever you would like to name it. Okay, initial condition. So now if we are now perturbing the system, by perturbing I mean I am giving some small signal to this system. So let us say that perturbing we are perturbing this with some voltage. Okay, so V1, it changes from V1 of 0 to some V1 of 0 plus delta V1. This is the small perturbation that we will be having. Okay, similarly, corresponding to V2, we will be also having some change, and it would change from, let us say, V2 of 0 to V2 of 0 plus delta V2. Okay, as simple as it gets. Now it would simply mean now my current I1 would simply be now a function of V1 of 0, okay, plus this delta V1, comma, it will also be the function of V2 of 0 plus this delta V2, and also the function of DC voltage, but this supply voltage is constant throughout. Okay, it would be constant throughout. So similarly for I2, we will be having the similar conditions. So this if now we use the Taylor series, so the Taylor series for this thing would simply be I1 F1 of V1 of 0, V2 of 0, okay, simple as it gets, and function of VDC. Now with these small increments, we will be having the terms which will be the differentials of these df1 with respect to dv1 at the quiescent bias, which will be v1 of 0 and v2 of 0. For example, this was our initial state, okay, into delta v1, which was the perturbation, simple, plus df1 by dv2. Okay, I'm just talking about the f1 in this case. Okay, for f2 we will be having df2 by dv2 and df2 by dv1 simply into, this will be into delta v2, and it will be corresponding to bias of v1 0 and v2 0, which will be initial state. Okay, similarly I will be having higher order terms, okay, like d2 f1 dv1 square at v1 of 0 comma v2 of 0 into delta v square, delta v1 square by 2, and rest of the higher order terms. But we want our amplifier to be to suppress the higher order, what we can say, frequencies. So we want our amplifier to be linear, so we always want that these additional frequency components that are present in the circuit, like that is delta v1 square times this df1 square, they should always be less. We can consider these components as some noise, and we should also always satisfy this condition in order to have this linear operation of these devices. Of our amplifiers, we should have this condition, that is df1 by dv1 at v1 comma 0 and v2 comma 0 plus df1 by dv2 at this times delta v1 v1 comma 0 v2 comma 0. This should be much greater than this df1 square dv1 square at some, let us say, this bias delta v1 square by 2 plus df1 square by dv2 square delta v square by 2 and plus rest of the higher order terms. So we want this thing, we want this, we need this, and this rest of the higher order terms are, all can say, these are junk for us. Okay, so if we now consider this first order approximation to that, for example, to that equation that we found out, this I1, for example, which was this I1, simply, this it would simply mean that this I1 is now, this I1 is simply now I1 of 0 plus some delta I1, and this thing, sorry, this term is simply I1 of 0. As you can say, as you can see these two terms, this is simply I1 of 0. Okay, it is simply I1 of 0. I1 of 0 plus df1, let us skip these delta v1 and let us ignore the higher order terms. So these will be associated with the frequency of like 2 omega naught and likewise 3 omega naught and greater. So we will ignore the higher frequency components, and we will say that this is our current, which we obtained in this device as a result of the small perturbation to the voltage. So it simply means that this delta I, which is the small perturbation in this current, is simply given by df1 by v1, okay, into delta v1. This will be having some frequency associated to it, this small signal, will be having some frequency omega naught associated to it, and this will be having some 2 omega naught, which will be higher order components, which we are not interested at all. Okay, plus df2 by dv2 into delta v2. Okay, so it simply means that this small signal current, which is at this initial condition v1 of 0 and v2 of 0, initial location like sort of thing, you can say this delta I1 is some small perturbation in voltage times the change of the function f1 with the with that small perturbation voltage. So if I write this delta I1 denoted by some small I1, it would simply mean this is some number which is named as y11. Okay, this is basically, you must have seen in like how these s parameters, y parameters, they are calculated. This is some equation or some matrix like that. It would allow us to go into the matrix form, and we will see that it is somewhat, not, it is y matrix. I wouldn't say somewhat, it is like y matrix. Okay, so basically we have this y11, which is this thing. Okay, and we have this y12. Okay, sorry, it should have been, sorry, it should have been df1. Okay, because we are looking into the function f1. Okay, so this is y11, this is y12 v2. Okay, this is the small signal delta v2 that we are representing with delta v2 with small signal v2 or small perturbation v2 simply. So this is for I1. I1 is simply some some number y11 multiplied by the small perturbation v1, and y12, which is some number multiplied by some small perturbation v2. Similarly, the I2, if we try to find out that, would also be function of this y21 v1 plus y22 v2. So if we write down this in matrix form, it is simply I1 I2 equal to y11 y12 y21 y22 times small perturbations, sorry, v1 and v2. Okay, these are the small perturbations, or this is the small perturbation that we introduced in that we had in our circuit, and as a result of that thing we had this small perturbation change in the output voltage as well. So it simply means that if I draw its circuit equivalent, if I draw this its circuit equivalent, it is simply, it will look like this thing. This I1, if this is the current in this I1, this is our small signal. Now this small signal circuit. Okay, I can say small signal analysis we are doing now. Okay, this is the small signal analysis. This is the I1. I1 goes into the y11. Okay, y11 times v1. Okay, this is our v1 voltage. Okay, so this is y11, and we also have the dependence of the input current. Input current also depends on the y12. It explicitly depends on this v2. Okay, it depends on the output bias as well. So we will write it like this. We will represent it by some current source y12 v2. So it is dependent on the output bias. Okay, output small perturbation that we had. Similarly, this I2 is similarly y21 and it depends on the small perturbation at the input. and Y22 is similarly small. This resistance which we will be having, and with this will be associated with this current I2, and this will be the V2. Okay, this is a signal, we can say, what I can say, two port network representation. Okay, you can see that this term transconductance is simply voltage controlled current source. Okay, transconductance, let us write it down like this: transconductance, simply voltage controlled current source. Okay, this is what we are having in the input side and the output side as well. Okay, this is just for the what I can say, purpose of illustrations, that this network, this equation in the matrix form can be represented by the its electrical network, which is given in this schematic. Okay, that I have, sorry, that I have shown. Wait a second, let me have some water. Okay, so now let us see that whether this circuit will give us some gain or not. What are the conditions in order to obtain gain from this small signal model that we have built? Okay, so if we now simply say that I am having some input Vs. Okay, I am having some input at the source, which is small signal, and I am having some resistance Rs. Okay, this model, now I connect it with this model, this Rs and Vs, and I connect some load at the output. I connect some load over here. Okay, and I connect some input over here. Okay, so I have connected this Rs at the input. This will be our positive negative V1. This will be our I1. Okay, this will be Y11, this will be Y12, V2, which is the output bias, sorry, not bias, this is the small signal output perturbation, Y21, V1, this is the Y22, this is I2, this is the load resistor. Okay, this is the RL. Okay, we are trying to drive this resistive load, for example, trying to drive the resistive load. Okay, resistive load. So basically, till now, till this point, we have been dealing in these resistances. It would be better if we skip this thing and we go to the rather to the conductances. Okay, if we deal in simply the conductances, so this Vs will become this will become some current source, Vs times Gs, Rs will become Gs. Okay, Y11, let us keep it as it is, Y11, since we are dealing in conductances. This is I1. Okay, sorry, what has happened to this? Okay, wait a second, this is Y11, this is our, we have Y12 times V2. Okay, I have this Y21 times this input perturbation V1 times this Y22 times this output load, which is now represented by the output conductance GL. Okay, as simple as it gets. So if now we try to see the input network and we try to use the KCL, I1 is simply equal to, sorry, it should be Vs times Gs, absolutely. So I1 is simply equal to it is simply equal to this thing. If some current is flowing in this is the current, it would simply be equal to this Vs times Gs minus times this will be the input perturbation bias, which will be this V1, which it will be simply this V1 times Gs. This is simply using the KCL, and I1 is also equal to this Y11 times V1 plus Y12 times V2. I have done a small manipulation that the incoming current is equal to the outgoing current simply. Okay, we have simply used that. From this we can write this Vs times Gs is simply equal to Y11, okay, plus not V1, plus Gs times the V1 plus Y12 times the V2. Okay, this is one condition that we will be getting from the input network. Okay, from the input network represented that we represented, and from the output we will be having this I2, rather I should say it like this is our I2. So this I2 is simply, sorry, okay, this is our V2. Okay, so this I2 is simply equal to I2 is simply equal to minus V2 times GL. Absolutely, yes, yes, it is minus V2 times GL is equal to, it should have the dependence of the Y21 into V1 and Y22 into V2. Okay, it should be Y21 into V1 plus Y22 into V2, or simply V2, uh, we can write this expression to be equal to Y21 V1 plus Y22 plus GL times V2 is equal to 0. Okay, we have got two equations, both function of V1 and V2. Okay, this was equation 1, function of V1 and V2, and this equation 2 is also function of V1 and V2. So let's use the matrix form. This was equal to Vs times Gs, and second component is 0 is equal to, the first component is y11 plus Gs, y11 plus Gs. Okay, second component is y12, and this is simply y22, sorry, this is simply y21. Yes, this is y21, this is y21, this is y22 plus GL. Okay, this whole thing multiplied by the row, the sorry column matrix, which is V1 times V1 and V2. Now in order to get this V2, what we would simply do, we will replace the second column, and we will just use the simple manipulation. I will just replace this second column with this thing. It will be y11 plus gs. You must have seen while solving the matrix, this is just the mathematical step, you shouldn't get confused with it. You can solve for v1 and v2 by using the linear equation as well and trying to eliminate for the v1 and getting it in terms of v2 only. What I have done over here, I have simply replaced this second column with this thing. Okay, now I will simply divide this by the magnitude of the determinant. Sorry, I would simply divide it by the determinant, which is y11 gs, y21 determinant v y12 y22 plus GL. This will be our V2. Okay, it would simply mean this thing is equal to 0. It would be minus y21 Vs into Gs. So it would be V2 would be simply minus y21 Gs into Vs, and in the denominator, sorry, we will be having y11 plus Gs into y22 into Gl. Okay, we will be having this y11 plus Gs into y22 plus Gl minus, we will be having this y21 into y12 into y12. Now this is the gain, for example, this is our output voltage, and the input signal in our case was this Vs, okay, that we applied at the source side. So this V2 by Vs is simply equal to minus y21 Gs divided by y11 plus Gs into y22 plus GL, okay, minus y21 into y12, as simple as it gets. Now our goal is to maximize this thing. In order to have the maximum amplification, we need to maximize this thing. So this can be simply maximized by simply, what can I do with this? I have the parameters like this GS and GL. GL is the output conductance. I cannot change this. I cannot change this GS because they are not in our control. What can we select or what can we go with? This is not in our control. These things are not in our control. So we have these y11, these y22, and these y parameters, which we need to look into. I can simply say that this, I since in order to maximize the gain, I need to maximize this y21. Okay, we want to, we can say, get as much current at the output. Okay, we need to maximize this, maximize y21. Okay, we need to maximize this. Let's not use this pen. Okay, we need to maximize this, or we need to make this denominator 0. But if we try to make this denominator 0, there is one problem. There is one problem that is associated with the oscillations. It would result in the, what I can say, it would result in the instability of the circuit. So the denominator cannot be, can't be 0. This is to avoid, sorry, what is happening with this pen, sorry, to avoid the instability. So we need to look into these other terms now. What we can do with the other terms? So this, if this denominator is 0, we will be having the unstable or oscillatory behavior. So in order to get rid of that thing, we say that this denominator cannot be 0. So what can we do with the other rest of the parameters that we are having, or rest of the y parameters that we are having? So let us say that this we can maximize this thing by simply saying that, what we can say that this, since this y12, we want this y12 to be 0. Okay, let me use another slide. So we want y12 to be equal to be 0. What is this y12? Let us check. Okay, y12 is the input current, what we can say, this how this output voltage determines or affects the input current. We clearly, for the amplification, do not want that our output should determine or how it should change our input. So we want this y12 to be equal to 0. One simple reason is that. Okay. Similarly, we want this y11. If I check this y11, we want this y1 and y22 to be also equal to 0 because we do not want the drops. Okay, we do not want the drops in these networks. Okay, we want this y1 and y2 to be equal to 0. So if these are all equal to 0, what we would get? We would get v2 by vs is simply this is 0. Let me use some another color. This is 0, this is 0, this is 0. So we will be simply left with y21 minus y21 times gs divided by gs into gl. Okay, it would be simply minus y21 into gs divided by gs into gl. This gs and gs will go, and this v2 by vs will simply be minus y21 divided by the output conductance gl. Okay, so in order to get the maximum gain, in order to have the maximum gain, what we require is we require this y11, y22 and y12 to be equal to be 0, and we want y21 to be as high as possible. Okay, we want this condition. We want that these y11, y22 and y12 should be 0, and this y21 should be as maximum as possible. Okay, we want this to be as high as possible. So this results in the simplified network. Okay, this results in the simplified network, which says that which we do, since we do not want the current division in the y22 and allow all the current to flow in this gl, this or this rl, this output resistance or the load. So we want the no input current division in at the input as well. So we have said that ideally our desired incremental model, let us say our desired incremental model of our amplifier, it should be like this. This should be the vs, the signal in the input that we are giving, the small signal. This is the vi. Since this y11 and y12 both are equal to 0, this will be the v1, this will be our v1. Okay, small signal incremental model. I don't know what is happening. This is y21 dependent on the v1. This is the gl. Okay, so this model, this is our desired incremental model. Okay, so basically what we want is we need this y11, which is simply di1, which is the change in the input current with respect to the input voltage. Okay, so simply at the quiescent, at the initial condition of v20 and v10 to be equal to 0, because we want infinite input impedance. Okay, similarly we want this this y12, which is y12, which is di1 by dv2 at this V1 0 and V2 0 to be equal to 0, because simply we want to eliminate intrinsic feedback. Okay, intrinsic feedback from this port, which was port 2 and 2 dash, to port 1 to 1 dash. So we want this Y21, which is the Di2, the change in the output current with respect to the input small signal change, incremental change, to be equal to V10 and V20. We want this to be as high as possible. Basically, this is our gain term. Okay, this Y21 is our gain term. And similarly, this Y22, we want this to be equal to 0. This Di2 with this Dv2, the change, this should be equal to 0 as well. Okay, so it simply means that our incremental model will look like this. This is I1, for example. This is I1. This is V1. This is Y21, V1. So this is our incremental model or small signal picture of ideal amplifier. Okay, ideal amplifier. So this is what the ideal amplifier should look like. Okay, so this I, with respect to the I1, it should be, for example, if I draw the plots, for example, with respect to I1, for example, this with respect to I1, it shouldn't change. I1 versus V1, which is di1 by dv1, which is y11, it should be equal to 0. It should be constant. I1 should not change with the v1. Okay, so this is one particular aspect of this small signal model that we have seen. Now, how is it associated with the MOSFET operation, in the whether we are operating the MOSFET in the saturation region or whether we are operating the MOSFET in the, or you can say, triode region. So now if we now use the MOSFET equations that we have been dealing all the time, okay, it would mean that let us see the MOSFET equation in the triode region or the linear region. Okay, so if I draw this simple MOSFET model, for example, and plot these y1 and try to find out these y parameters for MOSFET in saturation and this region, let me write it like this: find y11, y12, y21 and y22 for MOSFET in both triode and in saturation region. Okay, we need to find it in both the regions, and from that we can deduce which region we should operate the device in. Okay, now uh, let us say that we are using these equations, which are these this y1 and y22. Let us say that this is our model y11. Okay, this is this small signal gate to source voltage. This will be our IGS. Okay, this is the y12, which will be dependent on the output VDS, let's say, and this is our Y21, which is dependent on the incremental signal at the input. This is Y22, this is the IDS. Okay, so this is the VDS, simply, let us say. So now in triode region, let us say we have to find out this Y21. What is this Y21? Y21 is simply DI2 or DIDS by DVGS at constant VDS. Okay, which is simply D by DVGS. In triode region, the equation for this current is simply mu NCox W by L VGS minus VTH into VDS minus VDS square. Okay, simple as that. Oh, so what we have done, we have simply said that this is the Morse equation in triode region. So we will derivate this thing with respect to VGS. What we will get? We will simply get this to be equal to mu n C ox W by L into VDS. So it would mean that this Y21 is some linear function of this VDS. Okay. What about this Y22? Okay. We wanted this Y22 to be equal to 0. This Y22 is simply equal to di2 by dv2 or simply dids by dvds. Okay, so it would simply mean this equation mu n cox w by l, if I derivate this thing with VDS, it would be simply VGS minus VTH, and this thing will be minus VD. Okay, so it would simply be VGS minus VTH times minus VDS. So here Y22 is not equal to 0. So this is main problem in this triode region operation. We are not having this y22 equal to 0, and also we are having this y21 that we have seen. It shows that it has some dependency on this VDS. Now what about the other parameters? Considering the ideal what we can scenario, we can clearly see this gate current DIGS, which is the gate to source current. It won't change with the VGS. So this, because this IGS, this gate to source current, is 0. So Y11 and this Y12 would both be equal to 0 in triode region as well. But this Y22, what we found out, is not equal to 0 in this triode region. Now, what about this, rather I would say, what about our the saturation region? So in saturation region, we have simply this y1 and y11 and y12 equal to 0. We know that because this gate to source current is 0. Now what about this y21? This y21 is simply dids by dvgs. So it is simply in this saturation region, we know current is 1 by 2 mu n C ox W by L VGS minus VTH whole squared. Okay, this has to be divided by this VGS. This has to be differentiated with respect to the VGS. So it would be mu n C ox W by L VGS minus VTH. Okay, so in this Y21 we are having the dependency of this Y21 on the gate to source bias. This is what we need. We want this Y21 to have this dependency on the gate to source bias. What about Y22? Y22 Y22 is simply DIDS by DVDS, and it is clear from this equation, considering the ideal case only. Okay, ideal case is independent of VDS. Okay, no channel length modulation. Okay, so it would mean, since it is independent of VDS, it would mean Y22 is also 0. Okay, so in this saturation region we are getting all the desired functionalities, or all the desired parameters that we require for the operation of the power amplifier. So we require this Y21 to have this dependency on the gate to source bias. That is what we are having, and this simply means that this operating this device, operating the amplifier in the saturation region will be the beneficial for us in we since we want this VG, oh sorry, this Y21 to be higher for a given VGS, and for this, for example, in this previous equation which was this dependent on this VDS, this Y21 was dependent on VDS. So in order to increase the Y21 we needed to increase the VDS, and this for, but for a particular technology we, there will be this maximum VDS that we will be having. So we will be having this finite power supply limitation, and we cannot go beyond that. Okay, so we will be only having the option of this W by L that we will be left with in order to play with the gain. So in this saturation region, however, there is no this what you can say dependency. It depends on the VGS only. Oh, so this you can say that this also this Y22 was this equal to this in this region was in saturation region was equal to 0. So we can say clearly see that this for example, if I draw this simple, for example, this simple graph, if I draw the simple graph or rather plot for this Y21, this Y21 is equal to, simply it is equal to, in this triode region it is equal to mu times Cox W by L VDS, whereas in saturation region it is equal to mu n Cox W by L VGS minus VTH. So as we move from this linear to saturation region, we can clearly see that this there will be this plot will look like this Y21. If I draw its dependency with the VDS, it should look like this. Okay, then it would saturate at this is the region of mu n Cox W by L into VDS, and this is the region of mu times Cox W by L VGS minus VTH. Okay, so as we go into the saturation region, we will be having this maximum we can say VDS. So this Y21 it saturates when this VDS will cross this VGS minus VT mark. VTH is the threshold voltage. Okay, we want this Y21 to be maximum, so we want this transistor to be in the saturation region, which is as simple as that. And also we want this Y22 to be equal to 0, because this Y22 we do not want any current division in the between the load and the internal resistance. We want that the this we, let me write it like this, we do not want this any current division between this load network, or I can say between load network and internal internal resistance. Okay, so we want this y22 in 0, and this is in saturation region only. Okay, so what have we seen for this particular problem that we started with, that when used as an amplifier circuit, a MOSFET should be biased in which region? So it is now clear that the MOSFET should be biased in the saturation region, because it tends towards the ideality in this saturation region. The ideal behavior of an amplifier that we require for the operation of any amplifier, it has to be operated in the saturation region. We saw that how Y21 and Y22 are related to this the MOSFET current equations in the saturation and the in the triode region as well. And in both the cases, we found out that we need to operate the device in order to make it operational amplifier. In order to make it as an operational amplifier circuit, we need to bias it in the saturation region. So the answer for this problem is simply that we want to operate this MOSFET in the saturation region in order to have this amplifying behavior. And we found out this gain was simply equal to GM or Y. This actually, this Y21 is basically the transconductance, which is GM. Okay, it is simply equal to GM times the load resistance. It was simply that ideal gain that we will get from the circuit. Okay, so that was the picture of this MOSFET as an amplifier circuit. So now this, we can say this, what are MOSFETs? MOSFETs are simply these voltage control devices with high input impedance. Okay, we saw that we do not want any drop in the input network. We want all the signal that we are giving to the network, or this we are giving to this circuitry, we want all this signal to go as it is. We do not want any drop in its internal circuitries. Okay, so we want that this MOSFET model such that the input impedance is very high. That's why we said this y11 should be equal to 0. We do not want the this input impedance to hamper our functioning of this circuit. We want that the input voltage should control the output current. Okay, the input voltage should control the output current. So the option C seems to be the correct option. So what is this now? There is another problem which is associated with the same concept, although we didn't went in this effective channel length modulation in this lecture, but in the previous slides or the previous session, we had seen that how this channel length modulation can can be obtained, and how it is associated with the drain to source current, and how it comes into picture by multiplying by that term which we had seen, that 1 plus lambda VDS, that came into picture to the MOSFETs drain to source current. Okay, this dependency actually exists. The current also depends on the drain to source bias. Okay, this effective channel length modulation of a effective channel length of a MOSFET in saturation decreases, okay, with increase in drain voltage. This because we have seen in previous lecture as well how this pinch off region, it moves towards the source when the drain voltage is increased. Now let's move towards some problem solvings. We will solve some of the problems that we had left with in the previous session. And okay, what is it showing? Power connector is not plugged properly. Wait a second. There is some issue with it. Okay, now it's okay. Cancel this thing. Okay, so now This now there is some problems that we had left in the previous session which were associated with this small signal model. In this session, why we started with this saturation kind of a thing, because the first problem that we had to deal with was associated with the MOSFET operation. How we should bias this MOSFET, in what region we should bias this MOSFET in order to have the maximum gain, in order to make this work as an good amplifier, how we should bias this MOSFET. That's why we saw that we should bias this MOSFET in the saturation region in order to have this required gain that is desired to us. Okay, now it says that this problem says that we have this small signal resistance which is given by dVb by dId. Okay, we know that this will be some resistance which will be associated, which is offered by this N channel MOSFET. Okay, this is N channel MOSFET. Okay, this is N channel MOSFET, and this bias at a bias point, it is biased at 2 volts, and the transconductance parameter is given by this. The threshold voltage is 1 volt, and we have to neglect the body effect as well as the channel length modulation effects. So let us check the MOSFET operation first. This VD, let us say this VG is here equal to VB is equal to VD, okay, is equal to 2 volts simply. VS is equal to 0 volts since it is grounded, okay. So VGS is equal to 2 volts and VDS is equal to 2 volts as well, and VGS minus VTH is 1 simply. So VDS is greater than VGS minus VTN in this case. So the MOSFET, this is basically known as diode connected. Okay, this is known as diode connected. Let me write it like this: the MOSFET is diode connected. Okay, and is and in saturation, is saturation. Okay, this will also be true for these diode connected MOSFETs. So the what is this dVb by dId? Okay, it is simply dVg by dId. Okay, or simply it is equal to 1 by dId by dVg. Okay, or it is simply equal to 1 by Gm. dId by dVg is simply equal to Gm. So it would simply mean, let me write down the MOSFET equation in saturation region, MOSFET current equation. It would simply mean Kn by 2 VGS minus VTN whole square is ID. Now this dId by dVg is VGS or VG, whatever you would like to say, is simply equal to Kn times VGS minus VTN. Kn is equal to, sorry, it is equal to 40 micro. Okay, it is equal to 40 into 10 to the power of minus 6. VGS was 2, VTN was 1, so it is equal to simply 40 into 10 raised to power minus 6. Okay, or simply, since this is our GM, we know that we need to find out dVb by dId, which is 1 by Gm, which is equal to 1 by 40 into 10 to the power of minus 6, or 10 to the power of 6 by 4. Okay, so let us divide this. So it is 40, it is 10 divided by 4, it is almost equal to, not almost, it's absolutely equal to this 25. Okay, so it is absolutely equal to this 25 k. So it is equal to 25 kilo ohm, whether it is in kilo ohm, yes, it is in kilo ohm, yes, it should be in kilo ohm. So it is 25. This is the correct option to go with. We have selected the correct option. Now another problem which is associated with this MOSFET M1 and M2, both are NFETs, as is evident from this schematic in this picture. This is NFET, this is also NFET, and we have to, what we have to do, we have to first ignore this channel length modulation, and we have to find out the small signal voltage gain. Okay, but the thing is, we have been just given two W by L values. Okay, since we have been just given two W by L values, let us first draw its small signal equivalent. Okay, so that we get used to, although it's not necessary to draw this small signal equivalent every time, but since most of us will be doing it for the first time, it would mean that it is better to draw this small signal equivalent in order to build the concepts that would be good in the long run. So this is our V in, okay, it is like this, this is grounded, okay, this is this GM times V in, okay, channel length modulation has to be neglected, sorry, it is grounded as well, okay, and it is connected to M2, the source of M2, which will be having this, if this is GM1, this will be GM2, okay, it would be this V2, okay, V2, since this is grounded, okay, and this is the V out, okay, so this V out is what we are looking into. This is also grounded for the small signal model. So V2 is simply equal to minus V out. Okay. So from this, if I use the simple KCL, GM2 times minus V out has to be equal to GM1 times V in, or V out by V in is simply equal to minus GM1 by GM2. This is the expression that we should get. Now, how to get it in terms of W by L only? Okay, that is the main point now. Okay, let me write down the current equation in the saturation. Sorry, I don't know what's happening with this pen today. So ID is 1 by 2 mu n Cox W by L VGS minus VTH whole square. Okay, from this, if I write this VGS minus VTH, it would be simply equal to 2ID by mu n Cox W by L under the square root. Okay, now what is GM? GM is dID by dVGS. So if I do the derivative of this equation, it would simply be equal to mu n Cox W by L VGS minus VTH. Okay, now let me do some manipulations. Let me multiply it by 2 and divide by 2 and do the mu n Cox W by L, and now multiply this by VGS minus VTH and divide it also by this VGS minus VTH. Okay, this is what we have done. We have what we have done. We have, let me write it down in this bracket, multiplied and divided by 2 times VGS minus, sorry, 2 times VGS minus VTH. This is what we have done. Okay, so this whole thing is equal to equation 1. This is equal to ID. Okay, so it is 2 times ID, and this VGS minus VTH is simply equal to 2 ID under the square root, and this mu n C ox W by L, this is also under the square root. So this is GM, or simply GM. GM is equal to 2 root 2 ID mu n C ox W by L. It is simply equal to root 2 ID mu n C ox W by L. So now we have got the GM value. We know that the current in both the FETs, both the MOSFETs is same, ID is same for both, and mu n and Cox is also same. We have been given no information about that. The only difference is this W by L. So simply the gain we found out, V out by V in, V out by V in is simply equal to minus gm1 by gm2. Okay, someone wants to join the meeting. Wait a second. Okay, so it is minus gm1, so it will be w l of 1 by w by l of 2 with both under the square root, and 40 by zero point 0.5 divided by 10 by zero point 0.5. It is 40 by 0.5 divided by 10 by 0.5, which is simply root of 4, which is simply equal to minus 2. So this is our V out by V in. So the option B is the correct option to go with. Okay, we simply, what we did, we drew this, what I can say, this small, we draw this small, first of all we draw this small signal equivalent, and from that we got this expression in terms of this GM ratios. We said that in order to have this GM in terms of W by L, we will go and derive this W by L ratio, how it is dependent, this GM is dependent on the W by L only. So we came up with the expression which looked like this GM is equal to 2 times ID mu n C ox W by L square root. So that was about this GM thing, and then from that we simply said that the ratio will simply be equal to the square root of these two, which was root 1 root of gm1 by gm2. So it simply said that this gain came out to be equal to minus 2. Okay, now we have this MOSFET topology which is given, and it has been said that the MOSFET is in saturation and the current source is ideal, and we have been given that the GM is equal to 1 millisiemens. Okay, and the output impedance is 10 kilo ohms. Okay, this output impedance is 10 kilo ohms, and the RS is 1 kilo ohm. So what is the magnitude of small signal voltage gain? Okay, now if I draw this again, it simply look like this. It will simply look like this. This is our NFET. This is our source resistance RS, and we are having this 10k value of output impedance, which is 10k. This is our V out, and this is our current, which is Ix, which is coming into this terminal at Vx, and this is our another terminal Vy. Okay, because this the input current is 0 at node X. There is no because we are drawing the small signal equivalent, we know that the voltage source will be grounded and the current source will be open. So at this point we will be having no input current at the node X, and in order to obey the KCL, when there is no incoming current, there will be no outgoing current in the Y node as well. So the current in this case Iy should also be equal to 0 from simply KCL. Okay. Now this circuit will simply look like this now. It would simply be this MOSFET, which will be having some output resistance associated with it. Okay. It would be having some output resistance associated with it, which will be 10k. Okay, this will be the V out. This is our V in. So V out by V in will simply be equal to, its magnitude will simply be equal to Gm times the Rm, this RL value. So since this Gm is having the value of 1 millisiemens, it is 10 to the power of minus 3. RL is equal to 10k, it is 10 into 10 to the power of 3, or simply the gain is equal to 10. The magnitude of the small signal voltage gain is equal to 10. So we will select the option B that we have found out. So in now the second problem says that in question 1, if we change the value of Rs to 3 kilo ohm, magnitude of small signal gain will be, okay, we have to assume that this Rs value does not change the biasing, or what we can say, it does not move the MOSFET from the saturation to the triode region. It keeps it in the saturation region itself. But we have seen in this equation the Rs does not come into picture. The gain is independent of Rs. So the gain is independent of Rs. So it means that the option D is the only option to go with, because there will be the gain will remain same irrespective of the value of this source resistance. So it means that the gain will remain the same. Okay, if we change the Rs value. Now let's move towards another problem. It says that we have to sorry, I have not moved. It says to that we have to calculate the approximate magnitude of the small signal voltage gain by ignoring the body effect and the channel length modulation. So let us draw the I have repeatedly said, let's draw the small signal equivalent. Although you can do the problems without drawing the small signal equivalent as well, but let us draw the small signal equivalent first in order to get used to these kind of problems, so that whenever we see these problems next time or some sort of similar problems, we just by looking into its architecture, we would say that it should be like this. The input, we would just look into its input terminal and the output terminal, and we would say that the resistance is like this, the output resistance is like this, so the gain will be like this. So it is advisable at first to just remember or try to what can I say, logically infer these topologies in order to gain insights and expertise, such that you just by looking into the circuit say that this is this kind of a thing, and the input impedance should simply be equal to 1 by gm2 for this. Sorry, the impedance at the source for the M1 should be equal to 1 by gm2, which is evident from this circuitry. Okay, okay, so because we are neglecting this channel length modulation and body effect, everything. Okay, but since we are new to this field, let us draw this small signal equivalent for this. Okay, this is grounded, this is RD because we are considering a small signal equivalent, this is our output V out. Okay, this is gm1 times V in. Okay, V in is simply this bias, which is Vs of n, or which is simply Vs of p. Clearly this is the p FET. Okay, this is p FET, p type MOSFET. Okay, so this will be gm2 times V. This shouldn't be V in. Okay, let me write it down to be equal to V times Vg. Okay, S1 Vg is, this is V in. Okay, this is at V in, this is our gate. Okay, so this is grounded, the gate of this is also grounded, Vg2. So VGS1, so if I simply say this V of Sn or V of Sp, let us note it by simply V of S. Okay, so I would say the current Gm1 into V in minus Vs is equal to Gm2, this is VSG2. Okay, VSG2 is simply Vs. Okay, so this is our equation 1, and similarly the current would also be equal to 0 minus V out by RD is simply equal to this Gm2 times Vs, or simply I can write minus V out by Gm2 RD is equal to Vs. Now if I substitute this equation in this Vs value in equation 1, rather yes, it would be Gm1 V in times V, this is Gm times V in into Gm1 Vs Gm2 Vs. Okay, it would be Gm1 plus Gm2 into Vs, and Vs is having the value of Gm1 plus Gm2, and Vs is having the value of this minus V out by Gm2 RD, minus V out by Gm2 RD. Okay, so this what I can say, this V out by V in is simply equal to Gm1 Gm2 RD times minus divided by Gm1 plus Gm2. Okay, this is our V out by V in, or simply Let us put the values of the GM1 and GM2. It is identical. It is 1 millisiemens and RD is 10 kilo ohms. Yes. So it is minus. So let's basically concentrate on the magnitude, because it will be the magnitude which will be interested in, approximate magnitude. So the magnitude is equal to V out by V in is simply equal to, now this GM1 is 1 milli, GM2 is also 1 milli, RD is 10 kilo, it is 10 into 10 to the power of 3. So it's simply GM1 plus GM2 will be 10 to the power of minus 3. So this will go with this will go with this, it will be simply 5. Okay, this will be the voltage gain that we will be getting for this system or the circuit that we found out. So let's check the options. The option A is the correct option to go with, so we will take, or we will select the option A itself. Now let's move towards another problem which says that we have to consider the circuit which is given below, and it has these kind of specifications. What kind of specifications are given? We have this RD is given to us, the KN is given to us, and both the MOSFETs we have to ignore the channel length modulation. Now the bias of V1 is given to the MOSFET uh, M1, and to the V2 we have been given 0 volt. So if this is 0, this is also 0, so the MOSFET M2 is in off state because VGS is less than VT. VT is 0.8, M2 is in off state. So we have this M1 which is in what we can say, in some region of operation. Let's say that it is in okay. So let us find out the value for this current which is moving into this terminal, and since this is off, we will not be interested in this region, we will be interested in ID1 only, because this is simply equal to this resistance. The current in the resistor will simply be equal to ID1 because the M2 is in off state due to this VGS2 being less than VTH. Okay, so it would simply be this, using the KCL, 5 minus V0 divided by RD is simply equal to Kn, assuming the MOSFET is in triode region, 2 times V1. V1 is the VGS, okay, minus VTH into VDS. VDS is simply this V0 minus V0 square, okay. So it is simply 5 minus V0 in equal to, this is Kn is equal to 0.1 into 10 to the power of minus 3. Rd is equal to 20 into 10 to the power of 3, and 2 times V1 minus VTH. V1 is 5, VTH is 0.8, so it is 4.2. Simply it is 4.2 times V0 minus V0 square, or simply 5 minus V0 is equal to, this will go with this will go with this, it will be simply 2 times 8.4 times V0 minus V0 square, or it will simply be equal to V0 square, dividing everything by 2, it would be V0 square minus times 8.9 V0, and it would be plus 2.5 equal to 0, or simply V0 is a quadratic, it is quadratic in V0, and V0 will simply be equal to minus B, which is 8.9 plus minus 8.9 whole square minus this thing, which I would just calculate on my calculator. It would be root of 69.21 divided by 2. It is simply equal to 8.9 minus 8.32, because this cannot be greater than the VDD. That's why we have ignored this, what I can say, plus sign, divided by 2, and it would come out to be equal to, this V naught would come out to be equal to 0.29 volts. Okay, as simple as that. Now we need to calculate, what we need to calculate is the, yes, we have calculated the voltage 0.29 volts. Okay, for the another problem, okay, we also needed to calculate the voltage. So it is the same problem which is associated with the biases of V1 and V2, which is the same problem as this. Okay, so it doesn't matter if we solve this or not, because it should come out to be equal to 0.29 as well, because both the transistors are identical. So we have found out the voltage value. So if we are having some questions, we can entertain that. We will try to answer those questions, and if we are having no questions, then we can end today's session, and we can meet hopefully in the next session, where we will be solving the problems corresponding to each of the lectures that we have gone through in this course. So basically it would mean that most probably we will be having 12 different problems, which will be corresponding to each different topic or each different week that we have studied, most probably. So if we have some question, we can answer those, or we can try to answer those. So if we are having no questions, then I think we can end today's session, since we have solved all of the problems that I had assigned to myself in this particular lecture. So Aryan, if you have no question, we can end the session. Let me wait for your response for a couple of minutes, and if there is no response, then I think we will end the session for today. So I guess there are no questions now, and I should end this session. So thank you for joining this session. Hope to see you in the next session.